Good morning, everyone, again. Good afternoon now for everyone, I guess. So this is a very exciting session which we were discussing with Luna and Mahmoud and Professor Shah for a long time, and it was long overdue after the Chicago meeting. It was originally scheduled for this time of the year for the Chicago meeting in 2020. And after dealing with nanomaterials for all these years, it became apparent that the use of 2D nanomaterials can have very exciting properties and give us other functionalities that probably no one has ever heard before. The topic of my presentation today, I will deal with two particular sensing functionalities in concrete after, of course, we introduce to concrete carbon nanotubes and carbon nanofibers. There are two particular properties that we're very interested in. We have started a long time ago about measuring the stress-strain sensitivity, but we soon discovered that we can also take advantage of this stress-strain sensing and work on electrothermal efficiency. Both stress-strain sensing depends on the use of 2D carbon-based materials such as carbon nanotubes and nanofiber. They both gave us a great boost in exploring new functionalities, but these new functionalities deal mainly with the electrical properties and enhance the non-existent conductivity of concrete. Assuming that we have good dispersion and we can use them in concrete, these days we are able to fabricate the so-called semi-conducting concrete, semiconductor, that exhibits much higher than before electrical conductivity. Going a step further and assuming again that our 2D nanomaterial is homogeneously distributed into the cementitious matrix, into concrete, we can study now what we call electrothermal energy conversion efficiency, and this is the ability to convert the applied electrical energy into thermal energy. This phenomenon appears predominantly due to the flow of electrons through a conductive network when, of course, electric current is applied. It may sound very simple as a concept, however, taking into consideration the heterogeneous nature of concrete and all the difficulties for using and dispersing the nanomaterials, research on this subject can be quite challenging because we face we're dealing with many unknown factors. Nevertheless, there are three parameters here: the heating rate, the energy dissipation, and the dielectric loss tangent that are the key parameters that characterize the electrothermal efficiency of a material. Let's say of this specific material we're dealing, cementitious materials and concrete. Of course, the key to improving the electrical to thermal energy conversion efficiency is to increase all three of the aforementioned parameters. So, concrete's electrothermal energy conversion efficiency is the first functionality that I will be talking today. The second being the electromechanical impedance sensitivity, which refers to the semiconducting materials, stress-strain, self-sensing, and cracking detention ability when the material is subjected to mechanical loading. In this case, we will examine two particular properties. We will examine both the fractional change in capacitance, which we will be calling piezoelectricity, and change in resistivity, which is the well-known piezoresistivity. And I will walk you through to this process, and you tell me what do you think about how to evaluate the self-sensing ability of a material. A very important application for a material like concrete, having a high electrical to thermal energy conversion efficiency, that can be also of a great benefit for the concrete industry, airports, federal highways, is de-icing. Efficient and low-cost de-icing probably is a dream. Two of them together cannot go. The two of them cannot go together. And it will be a great benefit for everyone dealing with the ice. We have found 2 cases reported in the literature so far. The steel fiber reinforced concrete overlay on the deck of the Rochester Bridge over the Salt Creek at Lincoln, Nebraska, was the first implementation using conductive cementitious materials for de-icing. We show this in the figure on the left side of this slide. The authors reported with the application of 140 volts direct current, the conductive concrete exhibited an average heating rate of 0.04 Celsius degrees per minute, which is kind of low. The other case that was reported is in Des Moines, the Des Moines Airport in Iowa, and there we have cementitious overlays reinforced with 0.75% per volume of cement, carbon fibers at the micro scale, and a slab was fabricated. And this particular setup, under the application of 210 volts, which is extremely high, gave the researchers a heating rate of 0.18 Celsius per minute. Unfortunately, both of these cases, in both of these cases, researchers used direct current and high voltages, and although the carbon fiber concrete exhibits much better heating rate than the steel fibers, still both cases are under, let's say, under the occurrence of a thermal shock due to the application of very high voltage. In this slide, I'm showing you results of the heating rate of plain mortar and mortars reinforced with carbon and steel fibers, similar to the ones that the previous I have shown in the previous 2 applications. Obviously, the plain mortar, the ordinary Portland cement mortar, exhibits no heating rate, or maybe a negligible heating rate of 0.02 Fahrenheit per minute. We were expecting this. Of course, the cementitious materials are highly insulating due to the low electrical and thermal conductivity, and they exhibit very high resistance to electric current, and heat flow leads to almost no change in the temperature when current is applied. But look at the steel fiber reinforced mortar that exhibits a heating rate of 0.09. It's low. Of course, we used 140 volts to compare it with the previous examples. And our next curve, shown in green here, it's with carbon fibers, 0.75% per volume. The situation is better. They showed a better heating rate, but the voltage was extremely high. But nevertheless, they achieved a heating rate enough for de-icing. So this fourth curve I added in this figure concerns mortar mortars with CNTs, reinforced mortars with CNTs at an amount of 0.1% per volume. This is a very low volume for CNTs, but under this very small amount, we observe that we are able to induce about 1.5 to 3 higher heating rate. But please notice that now we have used a very low voltage of 2 volts. If we compare to the micro and macro scale steel fibers, carbon nanotubes and carbon nanofibers exhibit at least 3 orders of magnitude higher intrinsic electrical and thermal conductivity and great heat conduction. So maybe in front of us we have a material that can perform much better than the macrofibers, microcarbon fibers, and steel fibers. It goes without saying that the heating rate depends not only on the intrinsic thermal and electrical conductivity. Another parameter is the key here, which is associated with the amount of nanomaterials that can be included in the mix, and this is the degree of dispersion. The figure on the left side of this slide presents the heating rate for the ordinary Portland cement, which is shown with the blue line, and also the two mixes that include carbon nanotubes, the mix with 0.05% carbon nanotubes, which is shown with the orange line, and the mix with the 0.01 carbon nanotubes, which is shown with the red line, and it shows the higher heating rate. If you look at the percolation threshold graph, which is shown to the left, to the right side of this slide, you will notice that the amount of 0.05 CNTs is by no means enough to create a continuous network. And the electrons are transferred at a much lower rate in the matrix. Therefore, we do have a lower heating rate. If we double this amount, if we go to 0.1%, we see a great heating rate, and if you compare it to the plain mortar, this is an impressive increase of about 10 times, 9.5 actually. We have reached percolation, and we know that we're going to the right direction. We do have a continuous network, but the question here is what happens in this area around the percolation threshold. Should we use a little less or should we use a little more? In this case, we decided to go a little higher and to use 0.2%, just to make sure that the electrical network is continuous, and this way we can achieve a higher heating rate. But interestingly, we found that the 0.2 mix shows a lower heating rate. Looking back at the percolation threshold graph, which is shown to the right of this slide, you will see that we also included the capacitance value as measured by an impedance spectroscopy test. So it seems that while increasing the CNT content for amounts higher than 0.1%, we do see lower values of resistivity. But you will also notice that we see an increase in the capacitance value. So yes, we certainly have a continuous electrical network around the percolation threshold, which is totally defined by the resistivity values, but at the same time, capacitance values are informing us about the potential existence of either bigger in size or more CNTs agglomerates. Please keep in mind that capacitance values express the ability of storing electrical charge. So this is indicative of maybe a complete dispersion, but we do not know, but certainly an indication of an obstructed flow current through the established conductive network. Having said that, I would like to move on with what happens when electric current flows through the material, our material. Apparently, it results to energy dissipation in the form of thermal energy. we can represent the semiconducting behavior of cementitious materials reinforced with some conductive material, in our case, carbon nanofibers and carbon nanotubes, by an electric circuit consisting of randomly positioned resistors and capacitors. A resistor represents the component that opposes the flow, and capacitors have a structure like a fiber, mortar fiber, similar to that of a metal insulator, a metal capacitor. And capacitors represent the ability of storing the electrical energy. Both resistors and capacitors contribute to the heating of the material through two different mechanisms. The first mechanism is known as the resistive or Joule heating and is related to the resistive component of the circuit. The other mechanism is known as the capacitive heating, also known as dielectric heating, and is related to the continuously changing electric field. Resistive heating is introducing to us another important parameter, the energy dissipation, while capacitive heating, the dielectric loss tangent. I will start with results related to resistive heating. The conversion of electrical to thermal energy is called dissipation energy and is inversely proportional to the value of the complex impedance. Impedance is the complex number composed of the real and imaginary part that describes the opposition of the material to the flow of an AC current, alternating current. The complex impedance of a material varies with frequency. This is the reason variation in dissipation energy values is expected at different frequencies. To give you a better example than discussing different amounts of CNTs, here we are comparing two different types of carbon structures. We are comparing nanotubes and nanofibers. And keep in mind, please, that nanofibers have are a little less conductive. So the energy dissipation values of mortars reinforced with 0.1 CNTs are shown in red and 0.1 CNFs in green. And we apply the AC over a frequency range of 0.1 Hertz to 1 megahertz. We observe that carbon nanotubes are doing a better job and exhibit highest energy dissipation at all frequencies. The energy dissipation, as I mentioned, depends on the complex impedance of the material. And if you look at the inserts that we have to the right side of this slide, you will see the two different Nyquist plots of suspensions with CNTs and CNFs. And apparently, you see that the diagram for the CNTs shows the real part of impedance and also the imaginary part of impedance in the y-axis. So apparently, at the frequency of 100 kilohertz, the two arcs of the Nyquist plots intersect. The reactance value for the carbon nanotube is 0. And that indicates that at this frequency, the material acts as a neat resistor. It doesn't exhibit any storage capacity. So the neat resistive behavior of this material leads to high dissipation energy due to Joule heating phenomenon. On the other side, the CNFs, if you look at the 100 kilohertz, unfortunately, there is a value of reactance, which is approximately 25% higher. And at that particular frequency of 100 kilohertz, CNF reinforced mortars exhibit decreased dissipation energy values. The other property that I'm going to talk about today is the dielectric loss tangent.
Today you have 2 minutes.
2 minutes, the dielectric loss tangent. And loss tangent provides an insight about the energy dissipation capability relative to the storage ability of the material. From the equation we can use for the calculation of loss tangent, we observe that the loss tangent is proportional to the admittance, which it gives us a measure of how easily the current flows through the matrix. So the dielectric loss tangents of both materials are shown here, and yet we observe that the nanofiber reinforced mortar exhibits lower loss tangent than the nanotube reinforced mortar. And actually, we have an explanation for that, because the loss tangent takes into consideration the effect of interfacial polarization, which occurs with when there is an accumulation of charge at the fiber matrix interface. So here we included the results of our zeta potential values that are indicating to us that negatively charged atoms at the fiber surface can attract positive atoms, causing polarization, and this is more pronounced for the carbon nanofiber material. So interfacial polarization depends on capacitance. We have shown that, and the application, unfortunately, of higher voltages can create higher polarization values, and then at higher polarization values and higher capacitance values, then we can have the phenomenon of thermal shock of concrete. So I'm going to skip that because there is a relationship between capacitance and interfacial polarization. And I am going to give you one of the results for this talk, that if we want to tailor the electrothermal efficiency of concrete, we need to start with low capacitance values, then continue to produce high dissipation energy and dielectric loss tangent values, and there we can move on into high heating rate, but with the application of low voltage AC. These are the two keys that we need to achieve. I would like to show you now three very interesting results. It's been long regarded that piezoresistivity is actually the measure for strain sensing. So we conducted a few tests after finding out the importance of capacitance, and piezoresistivity apparently is piezoresistivity is a property. The behavior we can see is the change in resistance when we apply mechanical loading. So the results of the piezoresistivity testing of as received, meaning that we do not have any dispersion in the mix. You see in this slide, apparently we get no signal. There is no sensing with when we have as received CNTs, no matter how conductive the material is. But look what we get when we are measuring the piezoelectricity, which is the change of capacitance or the change of interfacial polarization during loading application. We get some signal, actually. So this is very important. This is very important because it gives us another tool for examining the sensing ability and the new functionality of the material. And here I'm showing you actual tests of monotonic compressive loading. These are without any dispersion. But look what happens when we have, as received CNTs here, the capacitance is giving us actually a mirror image picture of the stress strain curve. So we are very intrigued by that, and we continue our work on that. We still have a long way to go, but we are very excited about this. And just to conclude, I think I gave you the conclusions for the high electrothermal efficiency. The piezoelectric sensitivity is an ongoing work, and I will be happy to talk on about that on another talk.